Good afternoon, everybody. Welcome to this SMCB seminar series, Statistical Mechanics in Chemistry and Biology. This is the 16th lecture in this series, which has been running since March last year. So it has been about 1.5 years now. And the unique point about this seminar series is that we try to include the students, young researchers as much as possible. So we request the speakers to have a bit longish introduction so that the students get to know the subject and the new areas of research in statistical mechanics. And we already have, for those who are new to this group, we have a mailing list where the announcements of the future lectures are made. I'll also share the link in the chat later on. So if you are not part of that mailing list, I'd request all of you to join. And also we have a YouTube channel where recordings of some of the earlier lectures will be posted, and also some of the this current lecture as well. So whenever the speaker agrees to put it on the YouTube, we generally keep it there. So with that brief introduction, now I request Professor Ranjit Biswas, who is also part of this organizing group. So to kindly introduce our speaker for today, Professor Arnab Mukherjee. Ranjit, please.
Yeah, thank you, Shumon and Rajiv. It's very nice to have Professor Arnab Mukherjee from IISER Pune as an SMCB speaker today. With Arnab, I have some special connection because he joined IISc Bangalore in 1998. And that was the year that I was leaving, and probably he is the last person whom I took to Professor Bagchi's lab and introduced him to Professor Bagchi. Or no, I don't know whether he remembers or not. Anyway, then 2005, Arnab completed his PhD, got his PhD degree, and he moved to France to do his postdoctoral stint for 2 years in France with Professor Jetty Hines, and then another 2 years he moved to Colorado to complete another 2 years. And then 2009, sometime at the end, probably November, he joined IISER Pune as an assistant professor. In 2015, he was promoted to associate professor, and in 2021, he became the full professor. Arnab's area of work involves essentially biophysical chemistry, computational studies of various biophysical events that includes drug-DNA interactions, drug DNA binding, protein folding, and of course, he has done a very nice work on water entropy. The single water entropy is a very nice work, and today he would speak on this. In addition to this, he has moved his research. Probably he is now spending quality time on the utilization or exploring the applicability of machine learning or deep learning techniques into unfolding some of the complex biophysical problems. With this, I request Arnab to take the stage and deliver his talk. Arnab, please.
Yeah, thank you, Ranjita. I'll just share my slide now. So I'll share the whole desktop so that there is no problem. So it's okay, right?
Right.
Yeah, we can see it.
Okay, great. Okay, so yeah, thank you, Ranjita, for the introduction, and also thank you for the invitation. And I also like to thank Sumon, Rajiv, all the organizing members of SMCB. The series is running really great, and I'm fortunate to get the opportunity to speak here. And as we know that Professor Bagchi has already introduced this particular series to I think bring statistical mechanics related work into focus, especially among young students. So, and keeping that in mind, I think the mandate of this particular series is also to start the talk from a basic level and then slowly progress towards a particular topic. And previous speakers have done that beautifully. So I will also try to do the same. So today I'm going to talk about just 1 second. So I'm going to talk about my work on single water entropy, which I have been doing actually from the start of my journey at IISER. Before that, I think I didn't work on that. So when I started teaching thermodynamics, especially to the first year students here in IISER, I came across many beautiful things. And one of that is a famous quote by George Porter, Nobel laureate, in a BBC series. I only found one of them, actually. There are multiple, but only one I found in the internet, where he says that thermodynamics is a sine qua non of the scientific enlightenment. So it's an absolutely necessary thing to know for scientific enlightenment. And this is a beautiful quote that I start with. So entropy always intrigues people, mainly because it is there everywhere. Entropy governs the change. So the topic of entropy essentially is simple, but as I said, that it is intriguing, because one starts very simply with the transfer of heat from high temperature to low temperature, from the second law of thermodynamics. And it is defined by the simple expression of reversible heat change by temperature. When you bring hot body and cold body together, heat will flow from hot to cold spontaneously. That's also the second law of thermodynamics. And eventually it will come to be equal, where the entropy will become maximum. And we see that in many, many other processes. For example, the inequous process like phase change of ice, vapor, water, or carbon, graphite, and so different forms of polymorphism. We see that in the changes in the reactions. For example, when the sunlight gets converted to a chemical energy in our body through a process of chemical reactions, everywhere the entropy change is there. And a simple reaction like solubility, we talk about solubility equilibria, where solute dissolves in solvents, and that process is again governed by entropy. When we talk about processes like making a more efficient engines, then we know that in order to make more and more efficient engines, we have to reduce the entropy production. If we can convert more amount of heat to work, then the efficiency will increase. And that's where the entropy also plays an important role. So one common notion about entropy is that it is an order to disorder transition. So, or something that is becoming more chaotic, more random, that is entropy. However, there was a very interesting talk by Professor Sharon Gloucester, where she described a system of ellipsoidal particles which do not interact with each other. And the red color means they're in the disordered form. So I'll just play the video from our TED talk. As you see that as the time passes, spontaneously the order changes from disordered to ordered form. And since we know that it's a spontaneous process, therefore it must involve an increase in entropy. So this is an example where an ordering is happening along with entropy. So entropy doesn't always mean an order to disorder transition. That that's what she wanted to talk about here. So then, what is entropy in a simple form? And statistical mechanics explains to us. In my own understanding, entropy is nothing but more options. Or if I put it in a naive way, entropy is nothing but more options. If you have more options, there are more entropy. There is more entropy. So disordered state may have more options. Just bring my pointer. Disordered state may have more options, and it will correlate with the increase in entropy, but not always. And we know the famous formula by Ludwig Boltzmann that entropy is KBLN W, where W is the number of microstates in a microcanonical ensemble where all microstates are equally probable. So it's a statistical quantity. It's a thermodynamic quantity that applies on an average to a particular system. So every system, if left to itself, will on the average change towards a condition of maximum probability. Microscopically, there may be some reversal. There are talks about that. However, on an average, it will go towards maximum probability. So here is an example where a simple diffusion is happening. This movie is made by my student Raman. So initially started with 210 particle on the right hand side box, and as the time progresses, you can see from the bar also the particle spontaneously goes to the other box. There is no energetic advantage or anything, and they become equal. Now one can understand that by using a two-state model. I'm stuck here, 1 second. Two-state model where one can write W as n factorial by n1 factorial and n minus n1 factorial. There one can see that the W is more when the particles are distributed in both the sides, and depending on the value of n1, one can get many possible distributions. If n1 becomes 1, if one particle goes, that's a one distribution. If two particle goes to the other box and n minus 2 remains, that's another distribution. And what happens is that when n1 becomes half, then it goes to the most probable distribution where entropy actually becomes maximum. And Boltzmann has shown that most probable distribution is the distribution that will survive for a very large n. And one can actually take now, use the Boltzmann distribution to carry forward the rest of the calculation or rest of the work. So another way to look into entropy is essentially that it is the distribution of energy. So once you start with a certain amount or certain quantity of energy, certain amount of energy, with time it will spread, and that spread will increase the entropy. And that's what is happening all along. Now, how to calculate this? How to calculate entropy? So methods to estimate the entropy is, there are several methods. Experimentally, one can measure entropy using the simple thermodynamic formula. For example, delta G is equal to delta H minus T delta S. We know that that is equal to minus RT ln K equilibrium. And when we write this equation in terms of this second one, then if we plot ln of K equilibrium with 1 by T, then we can get delta S by R as y-intercept and delta H by R as. So we get both the enthalpy and entropy for a particular process from experiment. However, you can see that we will get it for a solvation entropy. So for example, if I start with water as a base system and I put some ions into it, then effectively we'll see a change, and that change essentially will be for all the waters that are affected by that ion. That means all the waters around that ion. So solvation entropy one can get. One, of course, will not get individual value of change in the water entropy. Ideal gas systems is a simple example. This is a general formula of entropy minus Kb sum over Pi ln Pi. And one can write, this is the Q is the partition function. This is the definition of the partition function. This is the definition of probability. And once you put this Pi into this equation, and then one can get this Kb ln Q plus this term. This is a very basic statistical mechanical starting formula. And for an ideal gas, one can approximate that by a particle in a 3D quantum box. Once you put it there, you will get a partition function like this, and you will get the Sackur-Tetrode equation of this particular form for entropy of a monoatomic ideal gas. So that means if I have n number of particles in a box of V, then the entropy will logarithmically vary with volume. Now, so this is for an ideal particle, ideal gas particle. However, that means there is no interaction among the particles. However, when we talk about an interacting system, when there is energy involved and all, then it will be much more complicated. Similarly, for rotation also, one can get from a rigid rotor expression the formula for rotational entropy. Now, we can also get, from our book, we can also estimate the entropy for a vibrational motion, where we can write the vibrational partition function. And so for quantum harmonic oscillator, and we can get an expression like this, where alpha is at the vibrational frequencies. So this is the expression that you can get directly from here, and that is also available in the book. But how do I get the alpha X? Now, we know that we can get from spectroscopy, of course. For water, for example, these are for 3 atomic system, we will have 3 vibrational degrees of freedom. And for water, this is symmetric, asymmetric stretch and bending. And their corresponding frequencies are also mentioned here. So one can use these frequencies to estimate the entropy of water, for example, water vibrational entropy of water using the previous formula. However, water is not just that, right? This is a simulation of water where one of the water is represented in a different way so that you can see this. And obviously, as you can see, that water is, moving all across the box, that also rotating. And of course, in this particular case, the vibration is stopped here because although there is bending, but we do not allow the bonds to move, depending on the water model, of course. So, so that means one has to account for translational motion and the entropy associated with that, rotational motion, and entropy and vibrational motion. Now, before I talk about how to calculate that, first let us understand why do we want to calculate entropy of water. Because entropy of water doesn't always mean that we are talking about the bulk water. So there is water in our body. Water, 70% we know that is in our body is water. And there are different percentages of the water in different parts of our body. But in a molecular level, especially in chemistry, water plays an extremely important role. For example, in DNA, we know that there is a spine of hydration around the minor groove. There is water, hydration shell water around proteins. And in the drug discovery, water entropy also plays an important role because this is a picture from water map. So where, let's say in the binding side, there is a very low entropy of water. So if you make a drug that will replace that water, then that water will go to the bulk. Bulk water entropy is same for both. However, if you substitute a low entropy water by the drug, then there is a gain in the free energy of the binding. So therefore, there were attempts to also estimate entropy of water at a particular site or at a particular location, because by doing so, one can presumably improve upon the design of a new binder or drug. I'm telling in a very general, loose sense, a new binder, we can say, to that particular receptor. So that was also our motivation to start, finding out how to calculate entropy at a particular site, particular location around a protein or around any other substance. So with that goal in mind, we wanted to see how to calculate the water entropy. Now, in order to calculate water entropy, first thing is to, of course, do the simulation, molecular dynamic simulation. And molecular dynamic simulation is essentially essentially integrating the Newton's equations of motions, where the forces will come from the derivative of the potential, and the potential energy may correspond to bonding, bending, and all that. I think this is, it's shown here schematically. This is like bonding and this bending, dihedral and non-bonding interactions. For water, of course, we don't have dihedral because there are 3 atoms, but we can have bonding, bending, and non-bonding interactions as well. So typically, 2 femtosecond time steps are taken if the bonds are constrained, and then one has to run for a longer time. Some processes, for example, intercalation is the key here, takes around milliseconds, which takes a long time for simulations. However, the focus here is just the water entropy, but that water entropy may come around a protein or a DNA and all that. So in that case, one has to simulate correspondingly that particular system. So in computer, one can calculate free energy, and by many different methods. Free energy perturbation is one of them. And one can estimate the enthalpy, and correspondingly one can get the formula, entropy by subtracting those 2. However, enthalpy is a highly fluctuating quantity, and therefore the error is large. Even in the entropy calculation, also error comes out large that way. There is also a received method called 2PT decomposition, where from the velocity autocorrelation function, one gets the density of states for liquid, which it gets decomposed into liquid and like solid-like and vapor-like density of states. And from there, one estimates the entropy of water. Goddard et al. Has introduced that, and Professor Prabal Maiti's group also has worked a lot on that. And then another method is quasi-harmonic approach, which is not probably that common, but it is common mostly in biomolecular systems. So again, quasi-harmonic approach I'm going to talk about just now in a moment. So what is quasi-harmonic approach? So in quasi-harmonic approach is that if you have a molecular trajectory, let's say the trajectory is given by x1t to xn, and then the configurational space of that, configurational space density will be provided by this particular density formula. And then one assumes the density formula to be a Gaussian. As you can see here, it's a harmonic potential. For an harmonic potential, like if the Vx is harmonic, then the distributions will be Gaussian, because you can put a harmonic potential at Vx, the distribution becomes Gaussian. But for a one-dimensional case, this distribution is for a multi-dimensional case. So that means if you have multiple variables, then one can approximate that as a multivariate Gaussian. You can see this is a typical harmonic potential, a protein in its stable state. This can be in a square wave potential, and there is a bistable potential here, where of course it is not Gaussian, but one can approximate that. When one approximates that as a Gaussian, which is not originally, then that approximation is quasi-harmonic approximation. So a little bit more on that. So this is the one-dimensional potential, and correspondingly the distribution will be Gaussian. And in the three-dimensional versions, one can write like that. Now, when you perform the, I can see some background noise. So when you perform, so now once we get a harmonic potential, then one can get correspondingly get the frequencies associated with that harmonic well, and that let's call that omega I. Now for a quasi-harmonic well, one can correspondingly get quasi-harmonic frequency, and then one approximates that using equipartition theorem to KBT, and by that one can calculate the frequencies of those quasi-harmonic well. I'll discuss a little bit more on that probably. And then using those frequencies, one can put that in the formula of quantum harmonic oscillator to get the entropy. So one is a harmonic frequency where, so typically people, when they calculate normal modes, they optimize that to the potential energy minima and then gets the frequencies. However, the effect of temperature and the environment will not be that well there, and therefore quasi-harmonic overcomes that. However, on the flip side, since we are using quasi-harmonic approximations where the underlying system may not be harmonic, one also needs to account for other corrections like anharmonic and mutual information entropy. So now this directly can be applied to protein and DNA, these quasi-harmonic approximations, because so if you run a simulation of DNA, then one can superimpose the DNA configurations over the time, and one can calculate the frequencies based on that. However, if you take water molecule, for example, and run a trajectory, that water molecule will be all across the box over time. So therefore, if you use the quasi-harmonic frequency calculations, then first of all, that will be meaningless because it will span all across the box. It will be very low frequency, and that may not, that should not correspond to the entropy of water. So for a diffusive system, calculation of water entropy using quasi-harmonic approximation is not feasible. So in 2007, Grove-Muller proposed a method called permutation reduction. So permutation reduction essentially assumes all water to be indistinguishable. Now you know that when you take indistinguishable systems, the partition functions will be divided by factorial n. So therefore, the configurational space reduces by factorial n. But in practicality, what happens is that a molecule which is similar in environment will club together. So for example, here, let's say initial configuration, these are the configuration of two water molecules, 1 and 2. But then in the next configuration or subsequently in other configuration, one moves up to this and yeah, so one moves there and 2 moves here. Let's say it was 2 before, now it has moved here, and it was 1 before, it has moved here. Now we label this one as 2 and label this one as 1. So essentially, we are not confining the water here. It is just relabeled as 1 and 2. So that after relabeling, one gets the water in a particular region moving in that region only. Now, this can be done. This is a linear assignment problem. So one has to map from n water molecule to the next n water molecule that n cross n similarity checks and see that which is similar to what. So this is an n cross n mapping problem, linear assignment problem. And that's how Burgmüller used it and showed the entropy of systems. However, you will get entire entropy of the whole system, right? So, but in our case, what we try to do is that we try to, so here also I'm showing the same thing. This is a 3-colored water molecule at particular reference frame. And then I'm, let's say, interested only in the green one. And then it moves in the next frame like this. Now, green has moved here, yellow has come there. So yellow has moved like this, green has moved like this, and blue and green has moved like this, and red has moved like this. Now, I assign this one as green and this one as red, yeah, this one as yellow and this one as red. So, however, my focus is only one of them. So I introduced asymmetric permutation. So instead of permuting n cross n, so all in water to a new all in water, we try to do n cross m. So out of n water, we try to permute only one water to the best possible configuration, best possible mapping. So where our aim is what? 1. So basically, we're focusing on one water permuting every time. So now you see that this water will preferably move only in a very small region. Now, it doesn't mean that, however, that region will be same for depending on the situation, and therefore we will get an estimate of water entropy. This estimate is not an accurate estimate. However, we are trying to hope for a linear correlation so that if something is lower in entropy, in reality, it should be lower in our estimate also. Just for an example, for a single water molecule of around methane, which started, let's say, initially here at this particular point and then moved all across the box, after permutation reduction will turn out to be only localized in this region. So basically, essentially, we are trying to get an estimate of water entropy in near methane in this particular region only. And then now we can assign average distance from methane to this particular blob of water. These are permuted trajectory, and can get the entropy of water as a function of distance from this methane. So this is a snapshot where several water molecules are individually permuted, and every color represents one water molecule across the trajectory. Not all the points, but many points are taken. Every color represents a different one. Now, essentially,
Arnab, sorry to interrupt. So if I'm Mithun here, if I want to estimate the error of entropy, what you said in that permutation approximation, so how to estimate?
So in our method, see, entropy, error in terms of what that we have to consider. So the way we calculate the error is by running, a kind of longer simulations to see whether the convergence have been achieved or not.
Okay.
Okay. So we run long enough, and we see that with time the value of entropy is coming to the same value or not, similar value.
But we cannot put an error bar in the. Can you put an error
no, so
bar?
again, as I said, that error
Okay.
bar is with respect to certain quantity, right?
Hmm,
There is an error with experiment, there is an error with other simulations, right? But there is no error for me to calculate for single water entropy, right?
No, but you are showing that for a long simulation, it converges to a certain value.
Converges to a certain
And
value.
around that value, can we put an estimate
Yes.
of error?
Yes, we can put an estimate of error there, which I did also. And also you can also put an estimate of error by running, let's say, 2 times the same simulations and then take an average and get it. Okay. So those are the standard ways of getting the error.
Right. Okay.
Now coming back to this is that, now let us discuss a little bit about that, what this kind of entropy corresponds to. Now I talked about, it may look like I'm confining the water. Again, I'm not confining the water. Waters are free to move. Simulations are done without any constraints or anything. Later on, it has been relabeled such that we get water molecules kind of localized because of the permutation in a region. Now, I'm using entropy of a vibration, formula for entropy of vibration, because this is kind of moving in a localized ellipsoid, as you will see, because since I'm calculating the frequencies along the 3 principal axes, it is essentially an ellipsoid. So, but the translation is essentially when the center of mass moves. Here, the center of mass of water, essentially oxygen, moving. So therefore, in a way, that is a translational entropy. But I'm using entropy calculations for a vibrational because it's a quasi-harmonic vibration in that well that we are talking about. So in a well, it is translation. So covariance matrix we calculate. So in order to calculate the frequency, we calculate the covariance matrix for all the points. So basically, for that, what you have to do is that you have to get the center of mass and then the difference and square, and then you have to diagonalize that covariance matrix. You'll get 3 frequencies. So this is that entire pipeline. First, you run the trajectory. After running the trajectory, you have to perform the permutation reduction of individual water molecule, and then mass weight it, and then calculate the covariance matrix of the mass weighted coordinate, which will essentially give you this particular one. And then once you diagonalize it, you will get the eigenvalues and eigenvectors. Basically, you are drawing 3. This is the PCA step, principal component analysis step. And once you do that, you're going to get the quasi-harmonic frequencies. Quasi-harmonic because in the whole framework itself, the assumption of the distribution to be Gaussian is already incorporated, equipartition is already incorporated, and we are getting at that particular temperature the frequencies of water molecule at a particular site moving with certain frequency. And once you get the omega, we just use this particular formula to get the entropy. So if I write in a different form, the same one, then I can show that it is essentially a function of temperature, and it is also a function of the logarithm of the volume. And that volume is the volume of the ellipsoid, where the values axis of the three axes are 3 principal axes, and those are mentioned as lambda i's. So larger the ellipsoid, larger the entropy it will be. And again, also it will depend on the temperature. So you get effect of both. So that was the translational entropy. And for rotational entropy, we follow the same formula as as was discussed by Lazaridis long back. So there we get the 2 Euler angles of water. We don't need the third one. 2 are enough. And one can calculate from, again, the PLNP formula. One can get the entropy of rotation, entropy of water rotation. However, again, this entropy is calculated for single permuted water. That's the only difference. So now we have the framework ready for calculations of water entropy at a single particle level. Now, before we do it for water, we just try to do it for, actually it is done later, but I can show you. So sometimes we might think that it does not have the configuration entropy. So this is the formula of Sacco-Tetrode equation in an ideal gas. And this is just shown at different volumes and different number of particles in. Now we calculated the same thing as a function of volume using this particular formula of permutation reduction for an ideal gas, and it has high.
Is it okay if you take questions in between?
Yes.
Okay. Shomok has
Actually, I
raised
cannot
hand.
see. I don't see.
Yeah. So I'll tell you if somebody raises hand.
Sure.
Shomok has raised hand. Shomok, please go ahead.
Yes.
Hi, Arnab. Like in the last slide, before you introduce the rotational entropy, you showed that when it is after the permutation reduction, you have these ellipsoids, and the volume is included in the formula for entropy. But how do you exactly like compute the volume?
So that volume is volume of the ellipsoid. Can you see my cursor?
Yes.
Volume is the volume of the ellipsoid, which is 4/3, and pi ABC. ABC is the three principal axes, length of the three principal axes, lambdas. So when I have the points, when I diagonalize that, I get three eigenvalues and eigenvectors, right?
Right.
So the eigenvalues are those axes.
I see. Okay.
Yeah. So and then we get an ellipsoid.
Okay. Thank you very much.
Yeah. So this is the formula ideal gas. So then we calculated. Actually, my student Sarath has calculated the entropy of ideal gas particles across different. So the temperature is kept at 300, N is kept at 1000 particles, but volume has been changed. And then we try to see that whether we get the similar value as a Sacco-Tetrode. So Sacco-Tetrode value is here, our value is here. Of course, they don't match. However, there is a 0.99 correlation with that. So which means that it can capture the configurational entropy, although it may not look like, because ideal gas has only configurational entropy and nothing else. So that's why. So yeah, so these are the box sizes that he has used. Now coming back to not realistic systems, but we wanted to use water entropy first to talk about hydrophobic crossover. So it's a famous paper by Chandler where he talked about that 1 nanometer length scale, where the entropy of water being less than the bulk below 1 nanometer goes more than the bulk around 1 nanometer. So we took methane particle, which is sigma, and then by keeping the same interactions as methane, we increase the size of the particles to up to 6 sigma. That is our model. And also we have taken artificially charged model also, +1 and +2. So with that, we calculated the water entropy for different sizes and as a function of distance. So first thing to note here is that as a function of distance, when the water molecule goes away, the value should be same. Value should be like bulk, the entropy of each water molecule. So every dot is a different water molecule's entropy. So as you see that when it is small, it is less. However, when the distance increases, the values become similar, and that is our bulk value. However, for a large particle, the closest water has higher entropy, and then it goes down. So somehow the effect of the bigger size is captured. In fact, we discussed a lot in this paper. There were theories about dangling hydrogen bond. We calculated that and showed that yes, it has there and all that. So, but this kind of shows that the conceptually things are working, as in that far away from the solute, all the values of entropy is same, but near the solute, it working differently depending on the size of the particle. Rotational entropy by constructions can not go above 1, so it is always like this, and because the way the formula is, and that's what we get. From low it goes to the normal value. So low entropy of water essentially because of the restrictions by the solute as a function of distance. Beyond this point, they are all same. Now, when you add them together, so this is our translational entropy, and green one is the rotational entropy. But translation plus rotation, 0 is the bulk water entropy. So we are taking a difference from bulk water. And as you can see that around 4 sigma, which is 3.7 into 4, roughly more than 1 nanometer, it actually crosses. It may be serendipitous, but we show that even at a single particle level, we can explain the crossover from less than bulk to more than bulk at around 1 nanometer. We went further and tried to estimate, since we can calculate now water entropy at a single particle level.
Hi, sorry to interrupt, Nilanjana
Yeah.
here. I don't have a hand raising figure, but I think at least I can't locate it. Just to clarify, can you go back 2 slides, please? 2 or 3 maybe. So this is translational entropy, right?
Right.
Functional distance from your hydrophobe. I presume those are different sized hydrophobes.
Sure. Yeah.
So you're saying that at low distances, the entropy is high?
Yes, higher than the bulk. So it reaches bulk at that.
But, we know from experience, we know from dynamics that that is not actually the case. If you're close
No,
to...
so the hydrophobic crossover essentially says that if the particle is hydrophobic small in size, then water will form hydrogen bond around it and entropy will be low. But as soon as the hydrophobe becomes bigger, that hydrogen bonded network is not going to be possible. Experiment has shown already that there will be a crossover from low entropy to high entropy for a bigger hydrophobes. And that is the...
get that. Could you try again?
Sorry. So that crossover is well known. That it from less than bulk to more than bulk, it happens around a certain length scale, and that is already mentioned in this Chandler's paper that I showed you here.
Okay, I'll probably talk to you again later on.
Yeah, definitely. Okay, so now let us talk about protein cavity. So we didn't stop just by calculating from this thing. We also try to now investigate individually the water molecules in a single protein cavity. That was, I think, much more challenging to do so. So in the streptavidin cavity, there is a biotin that binds very, very strongly. It's a well-known binder, strong binder. It has been used also in spectroscopy and others. So there are 5 water molecules that form a pentameric ring. There are actually 8 water molecules, but 5 of them form a pentameric ring. That is also well known. We wanted to individually calculate that, so we used our same method and we calculated. This is our estimate, and of course always we show the difference from the bulk because absolute value don't mean anything for us. So as you can see that for example this water number 4, it is I'm not showing the residue. Residues are also shown as part of TRP here. This water molecule actually loses the maximum amount of entropy, and the minimum is lost by something that is close to the setting. The point is that one can now individually calculate the entropy of water even at a single protein cavity. And we can estimate by summing up the total entropy change for water for binding to the cavity. And our estimate was similar to the other estimate made by Freshness group. Of course, not exactly, but more or less close. In this particular work, we also showed the contributions from anharmonic and mutual information entropy. Our rough estimate was 8 to 10% of anharmonic contributions was there, but mutual information entropy was even smaller. So subsequently, we did not do that for other future systems because it is much more time consuming to do so. Now, this was a hypothetical system, so one cannot get a real good sense that whether things are working or not. So we try to take realistic systems, and we this time took actual ions and polarizable water model, polarizable ions to calculate the water entropy. As you can see, we have taken both monovalent cation, divalent cation, and monovalent divalent anions and calculated the water entropy again as a function of distance from the ion. Now here also it goes and matches the bulk. Devashish has done that work, So it matches the bulk value. Now we can get 2 things from here. We can get now the solution entropy from here. Also, we can dissect that how much of that contribution is coming from first solvation layer, how much of that is coming from second solvation layer. Now, first and second solvation layers are distinguished by radial distribution functions. So we did that. Again, I'm not showing any of that, but we showed that again, 20% contributions of this solvation entropy comes from actually the second solvation shell. Now, when you plot the correlation with the solvation entropy, now we get individually all water entropy, right? However, we can add them up till it reaches the bulk value. Of course, it's a difference in entropy, so bulk value should not contribute. So when we sum up all of them around the particular ion and plot this, then we see a fantastic correlation with the experimental value of entropy. Yeah, so that kind of shows that this method actually can capture entropy contributions around realistic systems also. Now, we have now went ahead and worked on the supercooled liquid. Again, supercooled liquid is, you know, a lot of people work here. I'm not that expert. However, there is a debate about LDL and HDL, two, you know, liquids of two different densities, apparently in a very particular, you know, place, like, you know, the extension of LDA and HD, which are ice. And then extension of that gives to these two different density of water. And we wanted to see that whether that effect will come in our water entropy also. So, keeping that in mind, we try to work on that, and we varied different temperatures from 190 Kelvin to 330 Kelvin, 45p water molecule, and at constant temperature and pressure, and ran very long, like 1 microsecond simulation. So Devashish earlier had done that, and then now one of my students is also working on that. So initially, first of all, we looked into the diffusion coefficient, which is a well-known result of a strong versus fragile transition at a particular temperature. That was well known, but we wanted to see whether that kind of transition we observed for entropy also or not. And we do see a change in both the translational and rotational entropy around that particular time at a particular temperature for the supercooled liquid. I don't know how to interpret that as of yet. Now,
Arnab, does
yeah.
other methods of this is Sarika. Does other methods of entropy calculation also show that kind of a behavior in water?
Other methods, actually, I don't know whether they have done that or not. I have not tried any other methods.
Okay. No, because how is it? This need not be a single water entropy to be calculated.
Right. This is
like,
a solvation entropy, right? One can use other methods also to see, but either I missed it or I did not come across any paper, but I may have missed it also. I look for that. In fact, this is kindly old work, like 2017, so I'm a little bit off on that, but I can check. So, then we need to calculate the water entropy for only bulk water at a different temperature. Now, this is run by Sarath, my new student, for a very, very long time, microsecond simulation for each of them. One thing is noticeable, however, you can see that at a higher temperature, more or less the entropy is same for all the bulk water values. You know, the dashed line is kind of an average. But when you go to a lower temperature, then the values are kind of fluctuating around an average. And we were stuck at that for a long time. In fact, Devashish first observed that long time back. And we wanted to see the reason for this behavior. Is it because of less sampling? So if it is for less sampling, we really sampled for a long time. Actually, the convergence criteria was met, and then only we decided that, you know, it has converged. So, but we do see a distribution of water entropy for a low temperature, even for the bulk. And this is the rotational entropy also behaves the same way. I don't understand fully. We thought that, okay, let's correlate with LDL, HDL, and zeta parameter, as you know, is well-known parameter by Tanaka for distinguishing whether it is LDL and HDL. Zeta parameter is essentially the fifth water molecule, the water molecule that is non-hydrogen bonded minus the closest hydrogen bonded, farthest hydrogen bonded minus the closest non-hydrogen bonded water. So that's why the value also can be negative. Now, for a high density, the zeta value will be high. High density is essentially happens at the ice side, low temperature side. Low density is essentially low zeta, which is high temperature. At a high temperature, that's what is going to happen. So this is a plot of our zeta distributions. So by taking the high temperature one, so high temperature one as low density LDL and low temperature one as HDL, we can see that the bimodal distribution start around 240 to 50. The peak is bimodal. Now, whether to call them HDL and LDL is not clear. However, I know I just recently read the paper that came in Nature Physics by Shortino very, very recently. Of course, they have shown that at a very high pressure, around 1700 something bar, the high density, low density exists for T4P and T4PW water molecules. However, we are working with T5P, so I don't know at which pressure it will exist. However, we do see the distribution in zeta, and we wanted to correlate that with our entropy. And LSI is another quantity that calculates this particular thing. However, LSI, local structure index, that kind of also looks into the inherent structure that we are now going to do. This is not after optimizing the system to the local minimum. So maybe we'll see some difference with that later on. But one thing, if I just show you the entropy values, is 100 water have been chosen for entropy calculation for 190 Kelvin temperature. And we do see some average, and there are entropy of high value, more than average, and less than average. Now, if I pick the two highest entropy and two lowest entropy among these, and then plot their zeta distribution, we see a clear separation in their zeta distribution. Now, I thought that maybe the zeta is related to water entropy, and that comes up at a very low temperature. However, if we take all of them and calculate their zeta, there is no correlation. So this is all 100 points with zeta and translational water entropy. We don't see any correlation, which means that we have to still, this part of course is not published, so we have to still think about how to connect what is the origin of this high fluctuation of entropy even for bulk water at a low temperature. So that is still not understood. Okay, so I think with that I come to an end, and I would like to thank my student who first started working on single water entropy. Then Devashish has done also extensive work. Now Sarath, who is a BSMS fifth year student, he's continuing the work with that. And I would like to thank the funding from IISER DST, and thank you all. And if there is any question, I would be happy to answer them. Thank you.
Okay, thank you, Arnab, for an excellent presentation. I'm sure there will be lots of questions. Yes, we already see many hands going up. So Devdash first. Devdash, please go ahead.
Very, very nice and informative talk, Ananda.
Yeah,
so I have question on the crossover of entropy on that portion. Right. So it's like when you saw this crossover of entropy at some length scale, so is it related to that Loom, Chandler and Chandler theory of length scale crossover of hydration?
Yes, yeah.
I see.
Yeah.
So, and then another question is on slide number 40. If you go there, please. I can see that when you have a small methane molecule in water, the entropy is going down more than the water.
Yes. Yeah, I understand.
So like having a solute should somehow it should disturb the hydrogen bonding, and it should have slightly higher entropy.
It could be. We will still again look into that. So water around water is not a bulk water. That's the point that we wanted to show here. So when you take water as a solute, then the water next to it will actually reduce the entropy. But comparatively, it may depend on the interaction strength between them. Of course, water has hydrogen bonding, but also it creates a frustration. So we have shown that if we take with minus 0.5 charge, then, very hypothetically, then, it kind of increases the entropy. So because it forms, see, for methane, it is hydrophobic, right? So it tries to form hydrogen bond with other than that. So it has a preference of orientation. Whereas for water, it can form or may not form. I think that's why there is maybe a difference.
I see. And just one last question, sorry. So in the low density and high density water, like supercooled case, I think like trying another order parameter, like instead of zeta. Yeah.
No, so I'll tell you one thing. So recently this Nature Physics paper came. I just read today only, that's why I'm very excited about it. They have came up beautifully with some network-based index that clearly is separating and that is capturing the discontinuity in density, and that is clearly, so they're saying that highly entangled ones are the high density ones and low entangled ones are the low density ones. So we'll need to look into that for sure.
Yeah. Thank you. Thank you so much.
Yeah, thank you.
Okay, next is Brotin.
Hello, sir.
Yes,
Thank
Brotin.
you.
Yeah.
Thank you for this talk, sir. I have one single question. We apply enhanced sampling techniques in order to see the rare events, right? Like passing of an ion through the membrane or unbinding of a drug from its pocket. So during that process, so if we want to calculate the entropy, how we can calculate, because we are
okay, very nice. Yeah, very nice question. So is it finished? Question is finished, or
yeah, mostly, sir.
No, that's a very nice question. So how I would do, I'll tell you. I will go, I will take the reaction coordinate, some coordinate through which the unbinding is happening, for example, or binding is happening. Along that coordinate, at every point, I will do an equilibrium simulation. So this is an equilibrium simulation under a constraint. What is my constraint? Constraint is my reaction coordinate value.
Yeah.
Okay. So let's say this is my DNA, this is my drug. I will at this point, I will constrain it and do a simulation and calculate the water entropy. Then I will move it further. Again, I will do the simulation and calculate the water entropy. So like that, I will go along the way and I will calculate the water entropy at every distance along the reaction coordinate.
Okay, sir.
And that's how I will get it. Yeah.
So we are adding a potential, right?
Yes, simple. Let's say they take sodium and chloride. Then you move it by some few angstrom and then calculate the water entropy. Okay, by constraining them at that distance. Then it move it further and again calculate the water entropy. Then what you are essentially getting is that water entropy is a function of distance between sodium and chloride.
Okay, sir. So now my question is, like, we are applying that potential. Will it influence the entropy calculation?
No, this will not, because this potential is only acting on the solute. So this potential is it's a one-dimensional constraint in a three-dimensional system only to restrain that one. It is not affecting anything else. So they, as a pair, they will move. All other degrees of freedom is free. So therefore, it should not. It's basically putting a constraint on a particular phase space. So your observation is based on that constraint. So every thermodynamic parameter comes with a constraint. This is your constraint. With that, whatever you get is your value. That's what my understanding is.
Brotin, is that all? Okay, so maybe we can go to the next question. Sarikadi, please go ahead.
So, Arnab, I had a few questions, but let me quickly ask the supercooled part once. You see this fluctuation of entropy. So, don't you think that if it is a real, so you have done a similar calculation for ideal gas and you did not see a fluctuation, right?
Right.
Because these are for bulk calculation. The other
I did not even get for water molecule at high
temperature water. Right. So, so I think before doing anything else, the best thing should be to check with using other method of entropy calculation if this fluctuation is something real and universal for all entropy calculation method. And then definitely connecting it with a parameter would be a great thing. Like I'll later on talk to you, like you had that distribution of zeta and then maybe local structure, something if it can be studied, that also would be an interesting thing to do. One more question is that what Debashish, right? No, not Devdash. Devdash asked this question. That slide number 40, it was that water entropy and around methane with increasing size. Right. So this is your translational entropy, but you see an increase in entropy first, and then you see with size a decrease. So see, there are two information here. One is one single, if you keep a size same, what is the nearest entropy versus as you're going far away, what is the entropy? Right. Now, as you're going far.
Yeah, continue. Far away, everything is same because it's bulk, right?
Yeah, so far away is if you're going, is it like you're again constraining a water at a certain point when you're doing a far away calculation?
No. So far away when we are going, so we are picking up a water molecule that is far away from the solute, and we try to calculate entropy of that region. So you
yes, exactly. Yes,
so,
yes, that's
so
what I
that
meant.
region is unaffected by the solute, and therefore the entropy should be same beyond a certain point. Just like our energy should be same, entropy should be same. And that's what we observe for all the water molecules around all different particles.
Yeah. So does your ellipsoidal volume change when you go?
If it changes, we'll get different results, right? So which means that it does not change when you are far away from the solute. But when you are
I'm saying while you're close by to far away.
Yes, that definitely changes. Otherwise, it will not reflect in the entropy of the water.
Right. So it's a ellipsoidal volume also.
Ellipsoidal volume also changes because they are also done at same temperature. So CT function will not matter. Only the matter is will matter is Kb and V. That V is the volume of the ellipsoid, which essentially comes the diagonalization of the permuted water molecule, which happens to cover a larger space near a bigger solute.
Right. So that's the reason you're finding an increase in entropy.
Right.
The ellipsoidal volume, and also you see an increase in entropy as you're increasing. Say if I take the tip points of this all these curves, that is an increase in entropy.
No, that is the closest water. The tip point, let's say for this, that is the closest water. That closest water is the highest entropy.
Yeah.
And
then when you compare it with Chandler's result, you integrate over all this.
No, then what I do is that I now try to see for the closest water molecule what is the translation for rotation. So this is for the closest water molecule.
Right. So this is the closest water again, right?
Yeah. It's a single particle. The crossover is happening at a single particle level.
Right. And which is your translational one? The red.
This one.
The red
that is happening much faster. Rotation is kind of opposing it. On an average, overall, it is crossing.
So basically, So it is the rotational translational. You are getting
yes. It is kind of a serendipitous thing that it is happening exactly at 4 into 4 almost 16, 1.6 nanometer.
No, but you also have a reason. You can show that your rotation is decreasing, translation is increasing,
yes. And that is true. That is true. But it happens at 1 nanometer, 1.6 nanometer length scale is the one that is maybe.
That is interesting.
The construction of all these, the 6 sigma, 5 sigma, and all that we have taken. Potential we did not change. So naturally, it makes the water, interaction is weaker. Radial distribution goes down, the peak goes down. All that thing happens, right? So all that will give rise to that.
Yeah. Okay. Thank you. I think if I keep asking, I'll keep.
Maybe we can come back to you later. There are many more questions.
Yeah, sure.
So in the sequence, next is Shomok.
Hi, Arnab, thank you for the wonderful talk. So I don't know if I missed, but when you are talking about single particle entropy, then what about like two-body interactions or multi-body interactions? Like there should be a contribution from these
right.
components.
We did not consider that actually. So basically, you can say that this is a two-body interaction that has been considered. So see, I'll tell you. Okay, so let me reframe a little bit. So we did not specifically consider the two-body or multi-body. So when you do simulations, essentially you are having a pair potentials. So all interactions is a pair potential, right? So it's a two-body potential that is acting on the system. And that effect is coming through the quasi-harmonic calculation. We did not, but we could have done, because Lajeredy's work showed how to calculate three-body term and all that. But thing is that the contribution of a three-body term will be so small compared to even the anharmonic contribution that I did not take. In this particular case, I took, but later on, that I thought that it will not be. Here, we are not aiming for the accurate calculation, but how it behaves is more important.
So you mean that it is already inherent in the way the simulation itself
Yes, yes, simulation, but not again, like, not the three-body term and all that. Three-body term, one can calculate a three-body distribution and all, which we did not do. I don't think the contribution will be significant enough compared to already the error that is already there in this particular calculation.
Okay. Thank you.
Yeah, I see Professor Chandan Dasgupta has a question. Professor Chandan Dasgupta, please go ahead.
Yeah, can you hear me?
Yes, I can hear you, Chandan.
Okay, very nice talk.
Thank you.
So I had a question about basically application of this method to, let's say, dense liquids.
Okay.
And the question that I have is that, there this ellipsoidal volume will of course become a sphere, right? I mean, there's no anisotropy. I mean,
okay.
When you calculate.
So the thing is that apparently we may not be able to say. Do you have a strong reason to say that it will be a sphere? Because when we do principal component analysis, we essentially get three principal axes.
Yes.
And the depending on their eigenvalues, if they are all coming to be similar, then it will be a sphere. So ellipsoid is a more general term.
Yeah, of course. No, what you wanted to know is that this this volume or this ellipsoid or sphere or whatever it is, can it be related to something that people call cages? So if you have a dense liquid, a particular particle is basically in a cage which is provided by its neighbors. And this cage size changes as you change the parameters of the system.
Definitely, it is a cage, but how this cage here formed is an interesting question. So essentially it looks like as if it is caged, right? Every water looks like it is caged, but none of the water molecules are caged. Because
no, I know. They are moving, but you are bringing them back, basically, so to speak, by your permutation.
Yes. So essentially it is like caged. That is true. But it is caged by, it's an effective cage that is forming because of the way we are looking at the system through the permutation.
So typical dimensions of this, do you have any idea? I mean, how that looks
dimension?
Like? Dimensions of this volume in which this.
Actually, I should have known that. I don't want to also guess. I will probably email you later about that. Right now I don't want to guess. I knew it for sure, but it's a kind of an old word. But I will get back to you on that. Yeah.
In this case, of course, I mean, there is this methane sitting there and makes the system.
Yeah, you can see roughly the double the methane 4-5 angstrom. You can say 4-5 angstrom in one of the axes will be 4-5-6 angstrom. Not too large. But I should tell you the more or less.
Yeah, I mean, not particularly in this case, but in the case where you're looking at bulk system.
Yes, bulk system. Anyway, we have an idea, and this volume also will reduce. See, for example, I'd say when you look at this equation, right, this one. So let's say when you change the temperature, then not only CT term will change, but also the volume term also will change.
Right.
So we can see that how only the volume term changes with this thing. And high-dense systems, we did not try, but certainly I am willing to consider after reading today's paper a very high pressure calculation to go into near the HDL-LDL boundary.
Okay.
44P. That the pressure is around 1700 bar. So there they have located it. So we'll see there. I'm sure that there will be no problem for the system to work there. Actually.
No, I'd be interested in knowing how this volume changes, for example, as you go to a denser system or lower temperature and things like that.
Definitely, I will tell you that after doing the calculation.
Okay.
That is for bulk you're saying, right?
Yeah, bulk. Yeah, bulk.
Bulk with temperature, how it is changing, we'll be able to tell you. Definitely.
And what are the typical dimensions of this?
Definitely, all the lambda values will tell you that, right? So individually, we can tell you that lambda values. Whether it's a sphere or not, that is also an interesting question. That also we'll see.
Okay, thanks a lot.
Okay, thank you. Thank you, Dhananjay.
Thank you. Next, Biman Jana.
Yeah, Arnab.
I
was just thinking that this translational entropy you calculated, and you said that this is not exactly the value of the entropy you would expect, but there is a correlation with the real entropy value, right?
Correct.
So, and you're also getting a rotational entropy.
Right.
So, that also I think that will be correlated with the real rotational entropy in some way.
Right. Rotational entropy has no problem.
No, but when you are adding these two, can you really add that?
That again, it's a debatable thing. But since rotation and translations are independent, so I don't see any problem in adding them. Rather, you can ask me that can I add individual water molecules to get solvation water entropy or not?
No, that's a.
That I'm sure I cannot add.
Yes.
Okay, but here I think I can add. Because here there are two independent systems and entropy is basically an additive quantity.
No,
so
I know it's an additive quantity, but I'm just asking about the scaling, because
scaling
things can have different scaling, right? And
they can have different scaling, but apparently we have no way to know whether they have or not, because I'm talking about a single water molecule. Their translation rotations are two independent phenomena that are happening. So I just want to add them. I don't know whether there will be any weighting factor, as you were saying, for each of them or not. There is no a priori way of knowing that also. If I knew that, of course, one could.
Yeah, I know. That's why I'm.
So this is the first zeroth order approximation that one can take.
Because you try to add the two and then try to think about the.
See, the thing is, this is the zeroth order approximation, right? You know, you have to.
Yeah, I understand. Yeah. And also about can you go to that slide of the methane one? I just wanted to check one thing.
Methane translation, right?
Yes.
Yeah, here.
So the first plot you have water, right? The black one.
Right.
That means what you were trying to do here.
So we are trying to take water as a solid now.
So one water, then from
then onwards, we are looking at how the next water or next to next regions around that water is. It's like if you think about water.
Yeah, no, I got the point now. So I'm just thinking that this let's say for sigma, you get an interesting plot. It also seems like a PMA plot, right? Like potential of mean kind of plot.
Yes, you're right.
And some kind of dissolution barrier you are getting there. You are getting more entropy.
We also observed that. I did not pay too much attention to that, but your observation is correct. We are getting similar barrier also, just like what you expect in a radial distribution function. Similar thing we are observing there.
And the last part about that supercooled water, when you get the fluctuation, have you ever tried to see that entropy value wise, whether there is a formation of region of low entropy and high entropy spatially?
Spatially, okay. See, that's a very good point. Maybe we'll look into that. Initially, we tried to see that, single water molecule in the bulk water will not remain localized in a space.
Yeah, I know. There is a problem.
It is moving all the time. So we have also seen that the same water molecule goes through both, low zeta to high zeta value. Same water molecule.
I know.
So therefore, spatially resolving that one did not help. But I tried to do at least through zeta. And although we got some correlations spuriously by taking high values and low values with zeta, but when you take all of them, we don't get that.
So my question is here only that this number you are getting from a simulation of 1 millisecond or
one microsecond.
1 microsecond, right? And within that 1 microsecond, each water order parameter will change anyway from one state to other.
But we're doing permutation, right?
No, I know. But I'm just thinking that.
So our zeta value is for the permuted water molecule, not for the actual water molecule.
No, that's what I'm telling. So then how to really correlate this with the structural order parameter or something?
No. Yeah. So basically, let's say after permutations, I see, I get your point. So even after permutation, you are saying that they may go through
high
density, but I was hoping that all low density ones will confine to something, or high density one, but your point is very important that if the time window is long enough, then they might even switch and the zeta will be mixed up.
Yeah.
So that's a very important point. I have to look into that actually.
Okay. Thank you.
Okay. Thank you, Viman.
Can you change the time window for your
Yes,
permutation?
that's what Viman has given me the idea.
Yeah,
So,
that's what I'm noticing. That if you change the time window, then
so if I take like first 200 nanoseconds, next 200 nanoseconds, because it's very difficult to know when they are in what zeta value, right?
No, if you make within the alpha relaxation or some relaxation time window, then probably the value you are getting, you will find low entropy one is staging into a particular space.
I think, or another way is that if I can somehow confine them into that structure, then I can calculate the entropy and see that whether it's corresponding to that or not.
Might give you some interesting.
Yes. So that's what we will try then.
Yeah, a very short window calculation also gives you entropy. Right?
No, entropy convergence takes
convergence is a problem again.
100 nanosecond minimum. We have done 1 microsecond mainly for 2 reasons. One is that we have good computer now. Secondly, low temperature one takes more time. But high temperature 1 microsecond is not required. 100 nanosecond is enough.
Yeah. Okay. Thank you.
Okay. Thanks.
Thank you, Shushmita.
Hello, Arnab. Actually, somehow it is related to your ions entropy calculation. So my query is that many ions form hydrated ion. Right. So, and the first solvation shell of your hydrated ions are quite like rigid, and the dissolution takes like microsecond to millisecond of the order. Okay. So how are you exchanging in your method?
So see, the thing
like
is,
for example, magnesium.
Right.
It's a hydrated complex.
Now, see, the residence time of the water molecules we never looked into. What our method is basically simple. We run the simulation long enough, okay, around magnesium or any other ions, and then use the same method. Now, let's say it never exchanged. Then we will get very low entropy because that water will be always bound there. The ellipsoidal volume will be tiny because we are only talking about center of mass of the oxygen. Then essentially it will be just vibrating around that, and that correspondingly that will get the entropy value. But I don't think
it will not be a very statistically accurate entropy.
No, but when statistically accuracy comes from the fact that here we are talking about the water that is bound to magnesium. We are talking about the entropy of the water that is bound to magnesium. So you have to see that I'm not calculating solvation water entropy. I'm not calculating water entropy where magnesium is. I'm calculating around magnesium at a particular distance, what would be the value of entropy? Okay. So if you're talking about a bound water, that's what the entropy will be. And that will get from the simulation.
I got your point. I have another, I'm curious about that, whether you have analyzed some of the ions whether they can play, your entropy calculation can give an idea about whether these ions are water structure breaker or maker, or have you analyzed in that aspect?
No, actually not, because we were too much focused into water. A lot of people have
I got your point. Now method establishment is more important.
So we just wanted to see that whether our method is correlating with the experimental value or not. That's all that was our objective. So we were like, focused on that, just that. Yes, but it is an interesting thing that we can definitely look into that.
Okay. Thank you, Arnab.
Thank you, Susmita.
Thank you, Rakesh.
Yeah. Hello, Arnab.
Yes, Rakesh.
Yeah.
How are you?
So I'm doing well. Thank you. Yeah. So I have just 2 quick questions.
Yes,
first one is, that comment, just follow-up comment, like what Vivanda, asked, and also that like the interconversion, because here you have 2 types of time scales. One is the, like intrinsic time scale to your method, and second one is the LDL and HDL conversion time
Very
scale.
Nice,
and one can define, HDL and LDL like environment depending on your order parameter distribution that you got, like some cutoff on the based on order parameter. But from our experience, we know that that conversion between HDL-like and LDL-like environment usually happens on the time scale of picoseconds. So basically on the picosecond, you will see that, LDL converting to HDL-like local environment time probably.
It's a high temperature only, right? Not at low temperature.
No, even at 220 Kelvin or something, you will see that, like picosecond or hundreds of picoseconds. So that is, I think, much more faster compared to the time scale that that of intrinsic to the method.
Understood.
Right. So that type of possibility with the mixing.
Okay.
And the second thing here that you showed one plot that I still am trying to understand, that hydrophobic like PMF like trend that you showed here. Yeah. So this is you are calculating here water entropy in the close vicinity of the different types of methane.
Yes.
If I am not wrong. Yeah.
Yes.
So here I think this is bit like we understand iceberg formation around a small hydrophobes. You have like iceberg like structure, but when that type of local iceberg like structure forms, it decreases the entropy, like local entropy, of course. I mean, we are talking about like let us say first cell and second cell water molecules. So here one thing is that I'm noticing that it is increasing entropy, like very close to the
the hump in the middle, right? Like before going
first
that one
on the
right?
bulk, right? So that is going like against the iceberg model of like
these initial values, these points, right? See, these points, I also noticed that. See, this does not happen for ions. Okay, it only happens for this methane-like particles. See, ions never happen.
Ions, yes, definitely ions.
Yeah. So this one now I as you see that 2014, I did not really go back and check that.
Right. Okay.
But we also notice the same Q. But this is what our observation is. See, what happens is that it may not be. So the closeness, again, the way it is decided is the center of mass of that ellipsoid. Okay, it is not the closest water that comes. It's wherever the ellipsoid center is, that distance we put. Okay. So that is how we get the number. Whether it is the minimum distance, what is the minimum distance of the ellipsoid to the water, that maybe we could have looked into.
So there is some correlation here, like there is some correlation, like the minimum distance and the the distance of the ellipsoid that is there. And the second last question, actually, because already I think it's close to 5, that since you are observing the local entropy here, and usually we measure the local structure using some sort of order parameter. So I'm just trying to understand that in this particular case or other cases in general also, that whether it is possible to map or make some sort of correlation between your profile, because here it is a profile, right? Like entropy profile or single molecule profile. But whether this profile can be matched with the local structural change, like
that is what we are supposed to do, right?
Yeah, well, here in all right. So this particular case.
So that would be great, but I don't know as of now how to do that. So hopefully we can work something out.
Sure. Yeah. Okay. Yeah. All right. Yeah. Thank you,
Rakesh.
Thank you. At this point, I don't see any raised hand. I mean, extra raised hand. I'll ask a quick question myself.
Yeah, I just stopped. Stop sharing.
Probably it's a follow-up. So since there was some in Rakesh's question, he was talking about that very close to the surface, there is probably something that cannot be explained. But I was thinking that since you are using this kind of an ellipsoid approximate assumption, this model assumes that the shape of your water distribution is ellipsoidal. Now, very close to an interface, the shape could be truncated ellipsoid or of some sort, right? Because it's the distribution, whatever the distribution you have for a planar surface.
But whatever it is, there will be not a truncated ellipsoid. The ellipsoid would be of different shape, you can say.
Yeah.
Or rather, it is not at all an ellipsoid, but we are assuming
the formula for volume that you are using that may not be. That assumes the shape of a ellipsoid, right? But if it's a distorted ellipsoid, then would it the volume estimate would that still be valid?
Okay, I understood your question. So the thing is that we are not assuming that it is an ellipsoid. First point.
Right. Yeah.
Whatever the distribution of points are, by doing the PCA calculations, essentially we are getting 3 principal axes. Yeah. That means no matter what, we still will get an ellipsoid. However, that ellipsoid may not be the right shape.
Yeah, you mean it may not vibrate.
Shape. It can
both
be a box,
sides in
box, but we are just taking someone you're saying, right? It will be truncated. It may be a box, but we are still assuming to be an ellipsoid.
Right.
And that may be a problem. And what one has to do, that means essentially it is an harmonic contribution. Harmonicity gives you the ellipsoid. So anharmonic contribution one has to do. And for that, we have done this k-nearest neighbor calculation and all, where it will take care of that error. If that is there to some extent. And then there is mutual information entropy. Also, there is another contribution that comes. Once we add that, then it will be interesting to see whether we still get that anomaly near the solute or not. We have not done that, but this is just a thought.
Another technical clarification probably that you are permuting with only the nearest water molecules in terms of oxygen-oxygen distance. Is it the nearest water?
So you can say that and any other water molecule anywhere. So basically we can pick any water as a reference point and start permuting that water.
But the exchange, algorithm wise, what is the exchange that you are doing with the nearest water molecule, or how you are exchanging?
No, exchange is done with, so I take a system, I select which water molecule I want to exchange, permute, and then there is a sphere of other water molecules. At every time point, we see what is the water molecule that is nearest to the place the picked up water molecule was.
So in terms of absolute coordinate in the space,
it's like the space that is important, the region that is more important. And the region, if you don't select region, you are not going to get correct result. You have to select if you select water, you're not going to get correct result. So region is the more important. The region is not biased to anything. It is far away from the solute, so it will feel like bulk. But if you permute based on something else, then you are essentially permuting around the solute. So that is the technical thing that we have to go over it. But my point is that region is the key. So you can think about an absolute point x, y, z by keeping the solute as the center of mass, and at that absolute point, whichever the closest water has got level 1 at every time point.
So does it require so if you have a solute, then you can remove the, let's say, the translational motion of the solute, and you can put kind of an absolute translational coordinate. But what about the rotation of the
rotational case? We superimpose both the translation and the rotational degrees of freedom. We try
to. How you have to then fix the you have to specify that axis. Yeah.
Not fixing. We superimpose the translation and rotational degrees of freedom such that that solute, whatever they call it, that is not changing the axis. So we are, let's say, doing on amino acid, right? So the side chain of the amino acids is superimposed such that that amino acid is not moving, and then we can see the water arrangement around that. But while for doing the backbone, we have to do separately backbone superimposition, and then you have to calculate separately. That's a tricky part in that approach.
Okay, thank you. Is there any other question from anybody else?
Shimon, I had a question.
Yeah, please. Yeah.
Arnab, I'm just wondering, is this going to work in two special cases? One is, we know that when you have confined channels, you have the single file water motion.
Right.
So that is a clean case, I think. So I don't know how you will do this permutation with a bulk like water.
Very nice question, Ilanjana. Yeah.
The very nice question. One is, we have these interfaces where you have, let's say, a protein absorbing on a sheet or something. Okay, so there's perhaps one layer of water trapped there depending on the extent of hydrophobicity of your sheet. So those are extreme cases in my view. So I'm wondering if it's going to work in such situations.
Very interesting. So for ion channel, I have the same question. I thought of trying it, but did not do exactly for the same reason that you were saying, how it will exchange. But remember, still there will be some translational motion along the tube, right? Nanotube. So that translational motion,
in reality, they are actually trapped for a long time.
Right. They're trapped for a long time. They will have definitely very low entropy, but there will be some fluctuation because thermal environment, because it is after all happening at some thermal temperature, right? So there will be some motions, but essentially you are going to get very, very low entropy just because of the simple vibrational or vibrational motion of that center of mass of the oxygen and all that. And that's what my guess is. Now for water that is trapped between protein and interface, there can be exchanges happening by this from the point is that the method is not going to change, right? Method we are going to apply the same thing, but whether that method will yield the right kind of entropy trained or not, that is yet to be seen for this kind of spatial systems that you're talking about.
Okay, so I think the underlying assumption here is that your MD simulation has overcome all the kinetic barriers, whatever it is. So we have
even if it is not, see, point is that if there is a kinetic barrier, essentially you are getting the entropy corresponding to the well that you are in. If you cross the barrier, then you are going to get entropy corresponding to both the wells. See, when you're talking about protein folding and unfolding, if I have to get the entropy of both the states, then only I need to care about crossing the barrier of the folded state. Similarly,
talking of entropy, it's entropy in that local well that you're referring
yes, if you are
to,
trapped in a particular, that's I think that is one of the reason at low temperature we are getting such a high fluctuation. Because it is not being able to cross the inherent structure that is there. But that is a guess. That's why I didn't want to discuss there at length. But
I might write to you about a very particular situation.
Sure, definitely.
Okay, thank you, Arnab. Very nice talk.
Thank you.
So sorry, Arnab.
Yeah.
I can always come over and ask these questions at length.
Sure.
But I thought just one thing that, when you are at a very low temperature, then is it a possibility that, you can calculate an entropy really on a single particle without going through permutation? Like, because your time scale
Good point. Did not try. Yeah, that's a good point.
But
I hope that Sarath is noting down, because Sarath is the one who is.
So you remember we had discussed about pinned particle and
we tried that. We were not your point, your system, pinned particle.
Yes. So that time, so we did something with the 2PT method. Chandanda is also part of that manuscript. But you remember that time we had a discussion about using single single particle entropy calculation there. So I'll come back to you.
Okay, definitely.
Because I do have local entropy, local other method means not entropy, but local structure calculation that I'm doing.
Definitely.
So with that, we can do a comparison with entropy and see if
definitely. Actually, in fact, Anderson model Sarath was trying to do, but in between something else happened and we forgot about that problem. But anyway, we were also thinking to do for Anderson model and see whether things are working or not.
Yeah. You remember that time I came to you and we were discussing about the pinned particle system, right?
Definitely.
Okay. So I'll talk to you.
Okay. So I guess there is no other question or comment.
Who's there?
Is there?
Ranjita has question.
Oh, please. Yeah, go ahead, Ranjita.
No. Jokes apart, I want to ask Arnab that this entropy as a function of distance that you are seeing, what could be the indirect or direct evidences from experiments? Are there any experiments that provides you some sort of quote-unquote evidence? You can feel that it is there, but you are not really able to look at.
So basically, okay. So this question, I know it's, of course, it's not possible directly, but what I know, maybe you can tell me whether it is okay or not. Sometimes what happens that people try to increase the concentration of some solutes in the system, and as you approach higher and higher concentrations, your solvation environment essentially becomes fast solvation and things like that. So by varying the concentration and measuring the in solvation entropy, can we reach to closer and closer to the effect?
So the question is whether one can measure solvation entropy.
With a very high concentration.
Right.
But high concentration aggregation happens and many other things. So that remains again a challenge. But if it can be done, it can be done with the concentration in experiments. Right.
Thank you.
And also I think, Arnab, you have shown that the spectroscopic evidence, I think, right? How the hydrogen bonding environment changes based on.
Right. So I think that was some resonance Raman spectroscopy or something like that they use for this dangling hydrogen bond. And and Suman also, I think long back we discussed about the effect by lowering the temperature, something that I don't remember fully, but experiment, there is an indirect approach, of course, but maybe one can look into that. I'm not 100% sure.
The spectroscopy, the problem is that the energy that you need to excite falls in certain range where it is always there that it can excite a group of molecules over a certain distance. So by the time you are actually reaching the, for a large solute, you are reaching the bulk, you are probably covering everything. So that is one problem. Although in those Raman spectroscopy or vibrational spectroscopy, terahertz again, all these things are collective wave number measurements. Only the molecular level selection comes through you are exciting a certain band. But then you really do not have a way for space resolution. Exactly this energy and this length scale. That is not there. Okay. So again, there the simulations are the only way to understand what you see in experiments, and then probably you describe in terms of certain things which suits the explanation. That's all.
Sure. Thank you. Thank you.
So now if there is no more questions, yeah,
no, let me confirm. Is there any other question or comment? Anybody else? I guess not. Okay, so at this point, let us thank Professor Arnab Mukherjee for an excellent talk, followed by an extended discussion. It's always the good point of this seminar series that we get to have this kind of extended discussions, and also hopefully the speaker will go back with more ideas.
Yes,
so,
sure.
So let us thank Professor Arnab Mukherjee once again, and we thank all of you for being with us today till the end. And we'll announce the next seminar in due course of time, and sometime in October we are going to have our next talk, and we are going to announce that in our mailing list in our Facebook page. So watch out for that. Until then, I wish you all again. I thank all of you, and yeah, take care and goodbye.
Okay.
Bye. Bye, everybody.